Okay, so here's where we were last time. We were talking about doing integrals and spherical coordinates, and remember the big idea? It's change of variables. We're just doing a change of variables where we've chosen a particular function as our change of variables function. Namely, we're using the change of coordinates function for spherical coordinates. The tips and tricks to keep in mind, always slice in that order. Just in practice, in reality, I mean, what you're going to experience when you're doing stuff in spherical coordinates, this is all practically universally asterisk. Technically, there's a few exceptions. Practically universally the best choice. So just always do this, and it's extremely unlikely you'll have a problem. Second, your stretching factor. Don't forget the stretching factor. So easy to forget the stretching factor. We're going to be drawing pictures, trying to visualize things three-dimensionally, looking at slices and slices of slices. We're going to be very distracted with other stuff going on. Super easy to forget that stretching factor. The life hack, right, for not forgetting it is to always write this whole thing down all at once. Don't ever write down d rho d phi d theta by itself. Why would you? You're never going to have d rho d phi d theta by itself without a rho squared sine phi to accompany it, so why would you ever write it down? You're just taking a risk when you do that. So always write this down as if it's a single thing, which, by the way, it kind of is. This is dx dy dz, after all. Okay. All right. So keep all that in mind. And here we go. Diving into our first example. We have, you'll see here, a ball of radius A centered up on the z-axis so that it's kind of sitting on top of the xy plane at the origin. So, all right, how does this work? And keeping in mind our order of our differentials, we're going to do theta slicing first, followed by phi, followed by rho, but we're starting with theta. And so, this is what a theta slice looks like. Notice our theta slices just go all the way around. You might think of this, as what I like to think about it, is that our solid actually encloses part of the z-axis. And it's because of that the theta slices just go all the way around, 0 to 2 pi. And we can move on to the next bounds then. Okay, so what does a theta slice look like? Well, it's this half disc, I guess. And the problem with trying to make sense out of what's going on with this half disc, keep in mind we're going to be looking at phi slices of it. Phi slices look like this. Keep in mind the angle phi measured off of the origin, right, down from the positive part of the z-axis. Looks kind of like that, but now if you look at this angle phi, how we're seeing it in this picture here, we're looking at phi from an angle. We're not looking directly at it. This can make it confusing to see what phi actually is. So what I like to do here is to redraw that theta slice, looking straight at it, right? So here is the theta slice. This is what the actual cross section looks like. There we go. Phi slices of this, like that. And now you can see we're looking straight at the phi angle that we're trying to understand. I just find this a little bit easier to keep track of. You don't have to do this, but I think it helps. I think you'll find that it's just easier to make sense out of the phi angles. You redraw this slice for your consideration. Okay, so let's see here. Where are the first and last slices? Well, let's see here. The first slice right there, where phi is equal to 0. Everybody all right with that? Last slice is, well, we got to think this one through. Here's a slice, there's a slice, another slice. You can see these slices. As I get closer and closer and closer to horizontal, they get shorter and shorter and shorter and shorter. And I think you can see that in some sense the last slice is going to be at the horizontal is the moment that those slices kind of disappear. And any slices beyond that, any slices where I'm pointing, in any sense downward, swing and a miss. There's nothing down there. Our ball is entirely up above the XY plane. So, last slice is pi over 2. All right, and now we got to think about values of rho. Keep in mind we will be looking at our phi slices. Here's a generic phi slice. That is, it's a phi slice of the theta slice. Okay. And where do we start? Where do we end on this? Well, again, here we go. Here it is. First value of rho is at that point, which, by now let's remind ourselves what is going on there. What is that point? That point, aka that point, is actually that point, which is the origin, where rho is equal to 0. Right? And so our starting value of rho is 0. Everybody on board? Let's see, last slice, our very last, there we go. Very last point of interest is this point right here. And again, you got to remember, we're for our geometric convenience, we're looking at not exactly the right picture here. So we have to recall that point, aka that point, where that really comes from. It's really a point like here, on our actual theta slice, on our actual domain, right? And what can I say about that point? Well, it's on the sphere. So I'm going to have to figure out the equation of this sphere. And this is all chapter 1 stuff. Sphere radius A centered at 0, 0, A. We have an equation in rectangular coordinates. That's high school algebra. And then we can convert that equation to spherical coordinates. That's chapter 1 from this course. And that turns out to be this right here. By the way, make sure you can do this. Make sure you're comfortable, proficient, so reliable and quick, and always get the right answer, etc. Make sure you're solid on how to convert rectangular equations down to spherical equations. And now easy to lose track of what we're doing here. Reminder: why are we interested in that equation? Well, it's because I'm looking for rho bounds. That means that in this equation I need to solve for rho. Good news, it's already solved for. That's lucky. You won't always be so lucky. But in this case, then, rho upper bound is 2a cosine phi. And so that's it. We're done with this example. But notice how distracting it was. Drawing pictures, making slices, interpreting bounds, etc. Wouldn't it have been easy to accidentally come back at the end and put in your stretching factor? It's really easy to mess that up. Again, make sure to write this down all at once. Remove the risk completely. Right? So I urge you to make a point of doing that. By the way, just so you know, this stretching factor, it's from a grading point of view, it's a really big deal. From a multivariable calculus point of view, really, it's the main multivariable calculus concept in doing a spherical coordinates integral. Other than, some geometry and some algebra, things like that, this is really where the deep multivariable calculus concept is. So it's worth points. It can't not be worth points. It has to be worth points. And you can take 2 points of view on this. The cynical point of view is to say, it's a liability. I have to remember this, otherwise I'll lose a lot of points. That's the glass half empty point of view. Here's the glass half full point of view. Hey, easy money. Free points. All I got to do is remember to put this in here. And boom, points scored already. Right? So I encourage taking this positive point of view on it. It's easy money. You get all that easy money, again, just by remembering to always write this whole thing down all at the same time, all together, as if it's a single thing. Big win. Okay. All right. Now, y'all have heard me say the following a million times. I'm going to say it again. I just think it's a really big deal. A good picture is huge. It's just huge. It's very, very important. A couple of reasons. For one thing, it helps you make sense out of the question and how to answer it. really helpful to have a good picture, right? But don't forget, that is not the only purpose of a picture, nor is it the only purpose of all the other things that you write on the page. The reasoning, right, that gets you down to your right answer is part of what's required on an exam question or a homework exercise, what have you. So most of the reasoning, come back up here and look at what we just did here, most of the reasoning that got us to the bounds came off of the picture. I identified certain points that I understood as being part of certain surfaces and then took it from there. The picture was indispensably part of my reasoning. And you got to represent your reasoning. Right? So very important also from a communication standpoint, aka a grading standpoint, to show your picture as part of the reasoning. When you do make a picture, please don't make it teeny tiny. A lot of students like to make pictures about this big, little teeny tiny, little adorable little pictures, right? And the problem is there's so much going on, it'll get very, very hard to see what's going on inside of your own picture. So make it nice and big. Notice in what I've got on this exercise here, my picture was, that's a fourth of the page for the 3 different pictures I drew. Right. So don't be shy in making your pictures. Make them nice and big. Next, you might need to draw more than one. Your first picture might, despite your best efforts, might be confusing and cluttered. In fact, very often this is the case. It's also the case very often for me when I'm trying to figure out what's going on with we've got various surfaces. I don't know. Maybe I'll just draw these surfaces and maybe that'll help me get a point of view on how to think about what we're talking about here. And then from what I learned from that first bad picture, I can get enough insight to, okay, I see what this looks like, and then I can draw a better picture on the basis of the experience I got from the bad picture. So the revise and redo aspect of it, I think, is also really important. Last comment. There's techniques, there's tips and tricks on how to do mathematical drawing. Don't reinvent the wheel. Learn these little tips and tricks, little techniques. Couple of clever observations, and you'll instantly become a better 3D drawer. And then some of it, of course, is not instant, but some of it requires practice. The more you do something, the better you get at it. So I encourage you to find the tips and tricks. I have my advice, my best advice, everything that I know that I've been able to gather over, let's not say how many years in doing this sort of thing. YouTube channel, right on my miscellaneous topics playlist, 2 videos. I hope you'll find those helpful. And give yourself plenty of time to practice. Okay, moving along. So let's suppose we have now a different ball. This time, radius A, center again. Not at the origin, offset from the origin, this time in the direction of the y-axis. So this ball right here. Keep in mind, spherical coordinates is not symmetric with respect to the x, y, z axes. Z is special for spherical coordinates. So we should not expect this to be, kind of the same sort of thing as the last example. Here you go. Starting with theta. Here's what a theta slice looks like. The actual cross section that it makes. It's a disc, right? You take a ball, you cut through it with a plane, you're going to get a disc cross section. Everybody see that? Okay. For which values of theta do you get these disc cross sections? Now again, geometric appeal here, but I claim that it's sort of only what you might call the right half of XYZ space. In other words, only for positive values of y. You can see in the picture there, this ball has only positive values of y. And so only these values of theta, 0 to pi, are going to give you actual cross sections. Everything else is swing and a miss. So 0 to pi for our theta bounds. Alrighty, now then we fix a value of theta. Again, I like to redraw the theta slice. I just find it a little bit easier to see what's going on with phi. Let's think about our phi range now. Keep in mind, phi is an angle measured off of the positive part of the z-axis, something like that. And again, a little bit easier to see over here, like this. And I think it's a pretty easy pitch that this is what one of those cross sections looks like. Right, a phi cross section. So again, let's think about what's the range of values there. Again, just a visual reminder, we're looking at phi now. Well, phi is going to start from straight up, where phi is 0. And we're going to get these significant slices for all values of phi as we move along. It keeps getting bigger and bigger. No problem. We keep getting slices until they get shorter and shorter and eventually run out as we point straight down where phi is equal to pi. What do you think? Everybody buy it? Okay. So 0 to pi for our phi bounds. And now, as usual, we're going to fix now fixing a value of phi, looking then at a single phi slice. Note it's a phi slice of our theta slice. So with all of that fixed, now on to rho. And okay, well, let's see here. Rho. We start there, aka there, which is the origin, which is where rho is equal to 0. So rho starting value is 0. Everybody see how I got that? Ending value. Let's see. Let me just redo this. Here's our phi slice. Ending value of rho is going to be at that point. Well, wait a second. Don't forget that point. That's really this point over here, which, from what I can see on that picture there, is a point that's on that sphere. And so here we are again. We're going to have to understand this sphere. We're going to have to write the equation of that sphere, first in rectangular coordinates. Then we convert a la chapter 1. And so yada, yada, yada. I'm going to sweep all that under the rug. Make sure you can do this. Make sure you can get this equation right here for the the spherical equation of that sphere. It's, a little bit of algebra. Significant amount of algebra. Good practice. And then, of course, also don't forget that what are we here for? We're here for a rho bound. And so in this equation, you need to solve for rho. Lucky break, already solved for. And solving for rho, we get that as our upper bound for rho. Is everybody happy? Okay. Alrighty. Moving along. This last example is mostly here for a kind of a geometric artistic trick. I think this is a really good one. I like this trick a lot. First of all, let's talk about what our domain is. Let's see. Starting with this right here, notice we're looking at points outside of a certain sphere. There's the sphere, and we're looking at points that are outside of it. Yeah. And then let's see here. This here, we're looking at points inside of this sphere, and that's a different sphere, of course. It's this one right here. We're looking for what's on the inside of that. And now combine these two pictures, outside of the green, inside of the blue, and all together. Geometric appeal, as usual. We're talking about this thing right here. Kind of a funny looking hat, maybe. I don't know. There we go. Everybody with me? Now, the very first thing I want to do is I want to criticize my picture. My picture actually is kind of misleading. If you think about it, if you have a solid ball and then you take a solid spherical cut out of the bottom of it, there's actually going to be a kind of a circular lip going around, kind of like that. This lip is what is really the bottom of it. So why didn't I color in yellow all the way down to there? Well, because it's importantly, it's not solid all the way through. It's like it's got it kind of comes down on our near side here down to this lip, but then there's a cavity, but then there's more solid kind of on the back side. So it's weird. I mean, if I color in the whole thing, it makes it look like there is no cavity. If I don't color in the whole thing, then it makes it look like it's got points, little pokey little points on the left and the right. Neither one of those is correct. So it's a hard thing to draw well, is the punchline. And so with that in mind, it's going to be even harder then to think about cross-sections of it. And if I want to take, for example, a theta cross-section, if I want to cut this way through that solid thing, golly, it's hard enough to draw the solid, much less sort of visualize how is that going to slice at this weird angle. I don't know. It's artistically kind of hard. So here's the big idea. Rather than trying to understand this intersection, which is hard, and then taking a cross-section of that intersection, that's just geometrically hard, right? Instead, you can do the alternative as follows. Namely, look at the individual, what I'm going to call the individual cross-sections first. Forget about the intersecting. Forget about the fact that I'm doing something with these two balls. I'm looking at points that are inside of the one, outside of the other. Don't worry about that yet. Let's just look just at the two balls themselves. Let's draw their cross-sections. This is easy. This ball here, if I take its theta cross-section, well, this is no sweat. We've got a solid ball. We're taking a theta slice. It's half a disc. Just like another example we've already seen. That's easy to understand. Half a disc. And I can go ahead and draw that half a disc. Oh, whoops. Sorry, blue. Wait, blue? Yeah, blue. There it is. No problem. Easy cross-section to understand, easy cross-section to draw. And then let's see, what about the other ball that I have here? I have this ball like this. Oh, man, that was terrible. There we go, that ball there. It's another ball taking a slice with the same theta plane half disc. Again. And now, with my cross-sections understood, right, I've got these two cross-sections understood individually. They're just half discs. Now, let's take the intersection after. Right? After I've understood the two I see my cross-sections right here. And what's the intersection now? And by intersection, I mean what's, inside of the one and outside of the other. And, it's, you can see right here in this picture, I've accidentally drawn it already. It's that right there, in purple. There we go. Everybody see how that worked? I think it's an effort saver. It's a visualization effort saver and a drawing effort saver. So, big fan. I hope you'll consider this little trick. Will save you some trouble. Weirdly, it's easier to draw the cross section of the intersection than it is to draw the intersection itself. Yes.
Why is it the top part and not the middle part where they both cross over?
Well, okay, so keep in mind, I'm using the term intersection here. I'm not actually intersecting these two balls, right? I'm intersecting this ball with what's outside of the lower ball. And so likewise, when I get down to here, I want to take this half disc and then intersect with what is outside of this half disc. Does that make sense? Yeah. So, intersection suitably interpreted. So this part. Is everybody happy with the geometry? Is that all right? Okay, the rest of it's mostly the usual. I will point out that as you're taking your phi slices, again, here's a nice generic phi slice, and you're thinking about where is the last phi slice. You'll notice that last phi slice is at this point, and what is the value of phi at that point? Well, we get lucky again. Again, this kind of thing will happen. There's a very convenient equilateral triangle right there. And so that phi, the value of phi at that key point is, well, it's in fact exactly one of the angles of this equilateral triangle, and so it's pi over 3. Everybody all right with that? And again, if you really want to, you could write down the equations and do the algebra and solve for phi, and it's easier sometimes to just notice this. Okay, so that pretty much does it for spherical coordinates. There's a bazillion examples. We've done several here. There's more in the book. More in my past exams, of course. Don't forget about that as a resource. And let's move on now to part 3, as it were, of 5.5. Believe it or not, again, we're still in 5.5. It's just a ridiculously large section. I think this is a huge topic. The book doesn't push it as much as I like to. Most books don't push this as much as I like to. I think it is tremendously important. Symmetry theorems. There's some really nice theorems from single variable calculus that are even more valuable when you extend them to the multivariable setting. And so in particular, I hope you all remember this theorem right here. Talk through it in just a moment, but if you have an odd integrand over a symmetric domain, your integral is 0. Boom, and it's just a drop the pen and walk away kind of a situation. Really cool theorem. Hope y'all remember this from Calc 2. Odd functions, symmetric domain. In other words, where the negative k to k kind of a deal. Where in particular, where the interval is its own reflection. When you reflect over the origin, interval is unchanged. So very valuable theorem, but again, much more so in higher dimensions. So I want to just try to communicate how important this is, how useful this is by telling you from my own experience. So y'all have heard me say it a million times. I did a second major in college in physics, and physics isn't that different from engineering. And so those of you who are engineers are going to be looking at probably a pretty similar experience to mine, which was I did a ton of integrals over 9 physics classes that I took, right? I've sat back and contemplated, tried to remember the experience, and how often did symmetry theorems help me out with integrals? That from my 9 physics courses worth of integrals, and I don't have data. I can't give you an exact answer, but I what I'm calling a conservative estimate. It's about 20%. So 1 out of 5. So 1.8 physics courses worth of integrals. I was able to say 0 by symmetry. That's a massive number of integrals, right? It's a lot. This happens all the time in the physical world because the physical world is full of circles and balls and squares and triangles, things that have tremendous opportunity to be symmetric, right? So it's just extremely routine, lots of integrals. Rather than having to crank it out the old-fashioned way, very often you can just make a couple of key observations about oddness and symmetry, and boom, we're done here. Integral 0 by symmetry. So it's a pretty powerful trick. I think it's top of it's on the very, very short list of most powerful computational methods for integrals. Okay, so let's talk through it. Why does this work in single variable calculus? Well, here you have your symmetric domain, negative a to a. Keep in mind, you can think of this two ways. You can think of it as that these points are negatives of each other. I think better to think of it as an interval, which if you reflect it over the origin, doesn't change. Notice I'm drawing a graph here of our single variable function that we're doing a Riemann sum of. This term in the Riemann sum, right? F of that value of x times delta x. This term in the Riemann sum over here, f of that value of x times delta x. And keeping in mind that this function, by assumption, is an odd function, this height, or this, y value, this y value, the value of the function, they're negatives of each other. This is an odd function. And so at opposite values, these values are negative. So these terms in the summation are opposites. And so they cancel in the summation. And likewise for all the other pairs, right? This entire interval from negative a to a, they pair up and cancel, leaving nothing left. Nice point of view. Here's a arguably better point of view. Different. I claim you can prove it with a substitution. Y'all remember substitution from Calc 2. Calc 1, Calc 2, again, it depends on your course. And here's the idea. Because the interval is known to be symmetric, it is its own reflection. So I'm going to rewrite the interval as the reflection of the interval. Second, this now is an integral over an image. One of the things we've been focusing on in this course is that if you're doing an integral over an image domain, you can pull back. And substitution, as it's known in single variable calculus, change of variables as it's known in multivariable calculus, whatever, you're doing a pullback, and the image domain integral pulls back to an integral over the pre-image. Don't forget your stretching factor. We're talking, of course, just about a reflection, and when you reflect things, nothing gets bigger or smaller. Stretching factor is 1. And then lastly, don't forget that the function is odd. And so f of negative u is negative of f of u. Now, okay, I've been playing around with this integral. What does this buy me? What this buys me is if I look now at this equation, right, this thing I've been computing, integral over I of f, I now see that it is the negative of itself. And what, therefore, could this integral possibly be? What value? What is the only real number that is its own negative? It's 0. So, integral 0. Different point of view using change of variables. Which is why we talk about this in the section on change of variables. Is everybody on board? All right, let's see a multivariable version of this. Rather than reflecting over the origin, now keep in mind, in the last example, we were talking about one-dimensional domains. Just one coordinate. And the only kind of reflection, well, anyway, arguably, is just like this. Reflecting over the origin is really the only way we ever talk about that in single variable. In 2 dimensions, there's a lot more elbow room, right? It's literally an entire extra dimension. There's lots of different lines over which I might reflect, right? So we're going to talk in general now about a reflection over any line. And the reflection is, well, it's exactly what you think it is. Reflection is, given a point. The reflection is the point on the other side of the line such that that line segment is perpendicularly bisected by the original line L. Just like in the picture. Is that cool? Everybody buy this as a reflection? All right. Okay. So with this idea of a reflection noted, we can talk about odd symmetry. Odd symmetry, just like in single variable, means that if you reflect the input, you get a minus sign on the output. It's analogous to single variable oddness. It's just that now this could be any reflection over any line in the entire XY plane. And then we can also, again, talk about what it means for a domain to be symmetric over that line. And you just think through geometrically, but anytime you have a point in the domain, if the reflection is also in the domain, that's what it ought to mean for the thing to be symmetric. So think about like the Rorschach test, where the ink blot and they put down some ink and they do this move or they fold it over, right? And you get it always is a symmetric picture. And the folding is that reflection, right? The crease is the line L, the folding is the reflection. Okay. All right, so with all of this noted, highly analogous theorem here. Notice I've drawn it on the page to look exactly like the single variable theorem. It's a morally equivalent theorem. If you have a function that is odd and your domain is symmetric, game over, your integral is 0. Drop the pen, walk away. Effortless. You don't have to take any antiderivatives. You don't have to find any bounds. You don't have to worry about whether your bounds on the inside are sufficiently ugly that they're going to make the outside integral hard to do. No problem. Just odd, symmetric. We're done here. Victory. Isn't that awesome? I'm just doing an example in just a second here. Really, really valuable. A warning, though, both conditions have to hold. Very common mistake that I've seen students do over the years that I've been teaching multi is to see a symmetric domain and get excited about that and then say, oh, the domain's symmetric, integral must be 0. And it's not true. You need both conditions to hold. It's not enough for the domain to be symmetric. You must also have that the integrand, f, must be odd. Gotta be. So, very careful. Make sure to check both of these conditions. And I'm going to actually expand on that a little bit in a few minutes. Secondly, it's got to be over the same line. If your function is odd over one line and your domain is symmetric over a different line, no good. Doesn't count for anything. So this is another, again, very dangerous landmine. Please don't step on this landmine. It's very. The theorem, powerful as it is very delicate, and you do have to make sure to apply it only exactly as written. Okay. All right. So let me show you a nice proof. This is a lot like the proof on the previous page for the single variable version. If you have such a double integral, remember, domain being symmetric means that it is its own reflection. So if I replace D with the reflection of D, no problem. It's the exact same set. So, cool. Nothing changed. Nothing happened. Next, pullback, aka change of variables. Pulling back through the reflection. The domain being the image turns into a new integral with domain being the pre-image. That's how we do pullbacks. Don't forget to insert the stretching factor. A stretching factor, of course, is 1. We're just reflecting. When you do a reflection, nothing stretches. Right? This is not a funhouse mirror kind of reflection. This is just a regular, honest, bathroom mirror, flat. Things on the images on the other side are the same size as on this side. Okay. And then, of course, don't forget that our function is odd, and so the value at the reflected point is the negative of the original value. Or said differently, reflecting the input gives you a minus sign on the output. And again, same deal. Our integral is now equal to the negative of itself, and being the negative of itself, it must be the only real number that is the negative of itself. It must be 0. Everybody see how this works? More to the point, does everybody see this is exactly the same argument that we used in single variable? Right? Same argument. Symmetry, pull back, cite the oddness, boom. It's exactly what we do here. It's just a two-dimensional version of the same thing. And if you like, you can also think about it from a Riemann sum point of view. I'm not going to spend a lot of time on this. This is just for sort of believability purposes. But if you have a line and if you have a domain that's symmetric over that line, forgive my inability, so as the case may be, to draw this well. Pretend like that's symmetric. Then again, the terms kind of pair up and cancel. So this term in the summation and this term in the summation are negatives of each other because the function is odd, and that makes those two terms cancel. So just like in the single variable version, just one dimension up. Okay. All right, so let's do one. Now, I'm going to start us off, just for dramatic purposes, with an integral which, if I were to do it as written, would be a nightmare. All right? Wow, what a brutal integral this would be. It's got exponentials. Ooh, I see an e to the x squared in there. That scares me. Better or worse, I'm not sure, by that factor of x cubed. Maybe integration by parts, that may be a way to possibly, there might be a foot in the door there, but still, looks really bad. And then further complicated by the fact that our region has some weird boundary curve that's quartic, which means that our bounds for that inner integral are going to have, they're going to have a quartic in there, and that means that when I plug that in, even if I could do that inside anti-differentiation, when I plug in the bounds, it's going to just get horrifying. Right? So I'm very scared to do this the old-fashioned way. Here's how we're going to proceed. First of all, let's draw a quick picture of our domain. See if I can do a decent job here. Okay, so this curve I want this to look reasonably accurate. Something kind of like that. There's that curve right there. And first observation I'll make is that it is symmetric. It is its own reflection over the y-axis. Now, how do I know that that's the case? Well, you can, different ways you can think about this. You might just be persuaded by the fact that, x squared by itself is clearly symmetric over the y-axis, and x to the fourth is clearly symmetric over the y-axis, so the difference really ought to be. But if you prefer, notice we can write down a formula for the reflection. When I reflect over the y-axis, the only thing that happens is this minus sign right there. So you can think of reflecting over this y-axis as just introducing a minus on the x, and notice that turns the purple equation that we're looking at from that to this, which are in fact the same equation. Right? You compare the equation of the original curve and the reflected curve. These minuses go away because of the even powers. Nothing happened. This curve is its own reflection. Okay. And then let's notice the second curve there. Y equals -1, that's something like this. So our actual domain, now again, I'm just going to make an intuitive appeal, but this actual domain here, both of its boundary curves are symmetric over the y-axis, so this solid region is symmetric over the y-axis. There's a lot of geometric talk there. Does everybody believe that? Does that look reasonable? Okay, so we have a symmetric domain. Next, I claim the function is odd. How do I know the function is odd? Well, remember the rule. To show that something is odd, I need to compute the value of the function at a reflected point and have that turn out to be the negative of the original value of the function. And now, of course, you can see this algebra has worked out. F at the reflection is the negative of the original value of f. So this is what we want to show. But there's some things to think about in this process of doing this algebra. First of all, you do have to understand the reflection. Given an x comma y, I need an explicit formula for what that reflected point is, in this case negative x comma y, because I've got to plug that into my function to be able to confirm the oddness. All right? So, it's going to be different in every example we're going to do. This is what the reflection looks like over the y-axis. Different formulas for different axes, and again, we'll see more examples. Probably not today, but eventually. And the next thing to be aware of, and this is just kind of an annoyance, but this is again just the reality of it. When we're plugging this into the function, keep in mind there's our function, right? This f is this thing right here. When we're plugging in this reflection, that means that negative x, you see right here in what we're plugging into f, this negative x is what we're going to put in place of the x that we see up here. We've actually kind of sort of confused our variables. This is a little on the gauche side, and we could fix that, but in practice, it's easier just to think of it as negative x is what goes in place of x. So that means that our actual value of the function is this. And you'll notice then this negative x has been put everywhere in the original expression, everywhere that there had been an x. Does that make sense to everybody? Feel free to ask if you're uncomfortable. Okay, and then algebra. Make sure you already know certain convenient facts, like, so for example, the sine function. You can see here, I'm going to need to be able to rewrite sine of negative x. Very important to remember that we already know from high school trig that sine is an odd function. Right? So sine of negative x is the negative of sine x. Had to use that in this algebra. Okay, all together though, nice punchline, when you reflect on the input, you get a minus sign on the output. And that's what we mean when we say f is odd. Reflecting the input gives us a minus sign in the output. And we're done. We've computed this integral now, but it doesn't feel like we are done, but we are done. We've computed this integral because we have established that the domain is symmetric, the function is odd, this is over the same line, namely the y-axis in this case. Integral is zero by symmetry. Done. Walk away. We don't have to anti-differentiate anything. Thankfully, right? Look at this bear. I don't want to have to take anti-derivatives of that. I don't know if I can. Maybe. And then certainly don't want to have to take a second antiderivative depending on the slicing, and oh my gosh, super amount of potential to be a nightmare. And by comparison, zero by symmetry, much better. Okay. All right, real quick, I do want to say that there's a lot to these arguments. You'll notice these are the 5 things that I think are important in what I call a complete symmetry argument. You do have to tell me, in particular, what is the line of symmetry over which you're claiming a symmetry argument. I got to know geometrically, what are you talking about? Right, so give me the line of symmetry for sure. You're going to need the formula for the reflection over that line. Okay? So that's got to be documented in your work. You're going to need to note that the function is odd. Function needs to be odd. That's a very important part of the argument. You're also going to have to demonstrate that the function is odd. That demonstration is not trivial, right? Look at the amount of work we had to do here. The confirming the oddness was several steps, right? So that's real effort. You got to show me that in the on the exams, and then you also have to observe correctly that the domain is symmetric. And I am going to lax on the requirement here. You don't have to prove the domain is symmetric. Usually, if your domain is actually symmetric, it's usually pretty clear from the picture or from the algebra. And the way that you write that down, there's various different cases. I don't want to get into that whole ball of wax. This is not Math 222, 219. It's a little bit more. Let's just kind of geometric intuition, etc. So I think it's sufficiently clear when it's true that you can just state the domain is symmetric. That is, of course, assuming it actually is. Right? You don't have to prove that. Nevertheless, 5 things to show. And then the very last comment I'm going to make here before we won't be able to get to this example, but be super careful when you do a symmetry argument. And there's a reason for this. Powerful though it is delicate. It is easy to find cases where it's almost symmetric. Like the domain's symmetric and most of the terms of the integrand are symmetric, but one of them is not. And then crash and burn, and the argument just doesn't work. Right? So here's what makes that particularly dangerous. If you claim a symmetry argument, but the argument doesn't work, right? The function isn't odd, then not only do you have a mistake, but everything that you've written down in the direction of making a symmetry argument is futile. There is no symmetry argument to be made. So nothing you've written down is progress toward an actual solution. It's all doomed to failure because there is no actual symmetry argument because the function is not odd, for example. Right? So if you're going to use a symmetry argument, double check it, triple check it, make extra sure you've interpreted the domain correctly. Look back up to the statement of the question. Wait a minute, we're bounded by what curves now? Just double check your picture, double check your geometric intuition, make sure that the actual symmetry argument actually is valid before you dedicate yourself to that being your answer. Because if it's not valid, then nothing you've written down is correct. And that's it can be really tragic, scoring-wise. Okay, all right. So that's a good place to stop, and we will pick up here on. I was going to say Monday, but no, it's on after spring break. So 10 days from today. Y'all have a great spring break, and see you in a week and a half.